last time we talked about matrices, and matrices are really a tool. They're actually a tool in algebra. So you may have seen these before, and there's a wonderful course called Linear Algebra, which goes through and talks about matrices in depth. We're just going to really sort of scratch on the surface of matrices. There's a lot more that can be said, and we're going to limit ourselves in most cases. I don't want you to be panicking too much. We're going to stick to relatively small matrices. And so we'll channel our inner Noah and say, okay, 2 by 2. You know, that's what we're going to focus on. 2 by 2 matrices, and occasionally some 3 by 3. All right. But in general, what do we have? Well, we want to go through and say, now that we have these matrices, what can we do? So we're talking about differential equations in matrices. And you'll say, you know, I've seen a lot of these different phrases before. And so this is not like, oh my gosh, these are new concepts. It's like, oh, these old concepts are essentially the same. It's just a slightly new setting. So I don't want you to feel like, you're throwing lots of new stuff at us. It's like, oh, I've seen this before. That makes sense. That seems the right way to generalize. So what are some of these ideas? Well, one thing is, if we have a differential equation, x prime equals a of t, x plus f of t, there's this notion of homogeneous. That just means that there's no f of t, so x prime equals a of tx. And with that, we have a notion of superposition, which says, hey, if we have some solutions, then we can combine solutions together. And so that means I can take an arbitrary constant times the first one, an arbitrary constant times the second one, and so forth and so on. All right. So that doesn't seem so strange. We can also talk about the notion of linear independence, and that means the Wronskian. Because that's how we test. It's sort of saying, how do we know? How do we know that all these functions are really contributing something new? So I don't want to keep adding more functions if they're not making anything new. I really want to say these functions capture everything. So that's what that linear independence is testing for. And so we have a way to test. Now, the Wronskian is going to be done a little bit differently, because our functions aren't functions where we have numbers. Our functions are functions which are vectors. Our solutions are vectors now. So now, instead of saying, okay, the first row is function, the second row derivative, so forth and so on, we say, no. It's actually simpler now. We say, look, the first solution makes the first column. The second solution makes the second column, and so forth and so on. So each solution is a column. Now, there is a small technical thing, which is this can only make sense if the size of, well, I should say the number of columns you have equals the number of rows, because this is a determinant. Determinants only make sense for square matrices. But that's how we test. And the Wronskian does the same thing as before. Wronskian is non-zero, means linearly independent. Where the Wronskian is 0, things break down. And so we care about, hey, where is it 0? Where is it non-zero? What can we say? Well, now we say, okay, we know how to combine solutions. We know how to test if they're essentially distinct. Say, all right, if they are distinct, if they are linearly independent, then all solutions have this form. That's nice. So now we can say, hey, every solution looks like this. Now you might say, well, what about non-homogeneous? No problem. Same process as we did before. We find a particular solution, and then we have the complementary solution, and all solutions look like that. And remember, the particular solution says, hey, leave it to me, I'll handle the f of t. And the complementary solution says, great, we'll handle initial conditions. And what does that mean? Well, that just says, hey, not only do you know how you're changing, which is what a differential equation is, you know where you start, and so you can solve for your constants. All right, so these are all generalizations of ideas we've seen before. So the mindset is keep doing what we've been doing. Are there any questions before we try out some of these ideas in our new setting? Okay. Well, we'll jump right into the fire here, into the lion's den, if you will. Consider the following first-order system. So this is a differential equation system. That's the prime, meaning derivative. So x prime, we have a matrix here. 3 minus 2, 0, minus 1, 3, minus 2, 0, minus 1, 3, x. And then there's a part here. So this is our f of t. Minus 9t plus 13, 17 minus 15, minus 6t plus 7, with some initial conditions. X of 0 is 8, 21, 0. All right. By the end of today, we'll hopefully have finished this problem. No. We'll finish it before then. So we want to do a couple of things. All right. So for reference, just so we know what we're talking about, again, we already said this out loud, but we'll go ahead and write. That's f of t. And here's our a. Now in this case, I'll write a instead of a of t because a does not depend on t. It's our favorite type of system. In other words, constant coefficients. Okay, so there's some steps to do. It says verify this is a solution to the system. So we have 3t, 5, 2t. Now, what name would we have given this in our old setting? There is something in particular we would have said about this. It's a particular solution. Yeah. It's telling us, hey, that should be our xp. All right. So how do you verify something as a solution? Do you remember what to do? You plug it in. Wow. Great. Awesome. All right. So we're going to plug it into both sides. So we say, all right, what is xp prime? Now, we talked about this last time. The way you take a derivative of a matrix, which is also the derivative of a vector, is the derivative of each entry. So what's the derivative of this vector? 3, 0, 2. All right, so good. That's the left-hand side. Now, we're going to figure out, all right, what is our a, which is 3 minus 2, 0, minus 1, 3 minus 2, 0 minus 1, 3, times our x, which is 3t, 5, 2t, and add that to minus 9t plus 13, 7t minus 15, and minus 6t plus 7. Okay, so this is the right-hand side. All right, we begin. Okay, we'll start, well, at the beginning. Multiplication here. So, it's a matrix times a vector. This is the kind of operation you should get comfortable with because you'll see it again. So the idea is you're going to go along each row and simultaneously go along the column. So 3 times 3t, 9t. Minus 2 times 5, minus 10. 0 times 2t, 0. So it's 9t minus 10 is the first entry. Second entry, minus 1 times 3t. Negative 3t. 3 times 5, 15. Minus 2 times 2t. Minus 4t. So minus 3t plus 15 minus 4t. Well, that's minus 7t and plus 15. 0 times 3t. 0. Minus 1 times 5. Minus 5. 3 times 2t. 6t. Put them together, you get 6t minus 5. Plus minus 9t plus 13. 7t minus 15. And minus 6t plus 7. Now, how do we add these two vectors together? Entry-wise. Entry per entry. Okay, so when we add up the first two entries, the 9t minus 10, the minus 9t plus 13, the result is 3. The minus 7t plus 15, the 7t minus 15, the result is 0. 6t minus 5 and minus 6t plus 7, we get 2. Now, does this work? Well, you look and we say, aha, it's a match. So what does this mean? It's verified. Yeah. Once we see that, aha, both sides give the same thing, that's the verification. Life is good. We're 1/3 the way through our checklist. All right, good. We got the verifying in the bag. We got that? Nice. Next thing, verify, and now we have these things are linearly independent solutions to the homogeneous system. Now, when it says the homogeneous system, that says what do we do? So what equal to 0? The f of t. So the homogeneous system says, hey, there's no part here. The f of t goes away. So that says, oh, we're looking for something that looks like a solution to the part where there is no f of t. So in other words, it's the same beginning, but nothing on the end. All right, so that's the homogeneous system. Okay, now there's actually a couple of things that have to happen here, because there's two key phrases. One is solution. So let's talk about that phrase first. How do we verify that these are solutions? We plug them in. Okay, so which one do you want to do first? Probably the first one. Okay, so if we have 2e to the t, 2e to the t, e to the t prime, what does that give us? What's the derivative of that? 2e to the t, 2e to the t, e to the t. Aha, wow, amazing. Well, it's because the derivative of e to the t is e to the t. So that's not that surprising, maybe. And now we have, of course, the rest. That's one side. And now we do our multiplication. 2e to the t, 2e to the t, e to the t. Okay, so 6e to the t, subtract 4e to the t plus 0 gives us 2e to the t. Minus 2e to the t plus 6e to the t, subtract 2e to the t. So minus 2 plus 6 minus 2. So it will be 2e to the t again. 0 minus 2e to the t plus 3e to the t gives us e to the t. And now we check. Are they the same? That means that's a solution. Okay. We go to the next one. 2e to the 3t. 0 minus e to the 3t. Okay, and take the derivative. What comes out? 6e to the 3t. 0 minus e to the 3t. And now we also verify what happens when we multiply by our matrix. So it's 2e to the 3t, 0 minus e to the 3t. All right. Now, because e to the 3t is common, really just focus on the coefficients. That'll probably help. 6, 0, 0 together makes 6. Minus 2, 0, plus 2, 0. 0, 0, minus 3, minus 3. All right. So, do they match? The 6e to the 3t 0 minus 3e to the 3t match 6e to the 3t 0 minus 3e to the 3t. Yes. Okay. Wow. Now you're probably thinking, we're only 2/3 of the way done with this part. That only gets us halfway through this bullet point. This is fun. Look at all the math we get to do. Okay, what's the derivative of 2e to the 5t minus 2e to the 5t e to the 5t? 10e to the 5t. Negative 10e to the 5t. And 5e to the 5t. Okay. And the good news is, I think this will be our last time writing down this 3 by 3 matrix. So 3 minus 2, 0, minus 1, 3, minus 2, 0, minus 1, 3, times 2e to the 5t, minus 2e to the 5t, and e to the 5t. All right. Again, focus on the coefficients, because since everything has e to the 5t attached. 6 plus 4 plus 0 is 10. Minus 2, minus 6, minus 2. Minus 10. 0 plus 2 plus 3, 5. Do they match? Yes. Okay, so we have now gotten to the point where these are solutions. Are we done with our bullet point? What's missing? Got to check linear independence. How do we check linear independence? The Wronskian. Ah, the Wronskian. Hello, Wronskian, our old friend. It's great to see you once again. So, the Wronskian, we're going to take a determinant. Each function is its own column. Column. So, we write down the first function, 2e to the t, 2e to the t, e to the t. We write down the second function, 2e to the 3t, 0, minus e to the 3t. We write down the last one, 2e to the 5t, minus 2e to the 5t, e to the 5t. All right. Now, I hesitate to say something here because I think it's easy to confuse you. All right, let's do the answer, and then I'm going to point something out afterwards. Okay, so do our diagonals. 2e to the t times 0 times e to the 5t, 0. 2e to the 3t minus 2e to the 5t and e to the t. So 2 minus 2, 1 are the coefficients. Which gives us minus 4 times e to what power? E to the 9t. 2 e to the 5t, 2 e to the t minus e to the 3t. All together will become minus 4 e to the 9t. Okay, so we've done one direction, but as you know, there's always other boy bands. Oh wait, no, that's something else. Other direction. Okay, e to the t, 0, 2 e to the 5t, we get 0. Minus e to the 3t minus 2e to the 5t times 2e to the t, all together, it would be 4e to the 9t, but we have to subtract. Because remember, we have to subtract going up. Yes? Okay. We're almost there. We're in the home stretch. E to the 5t times 2e to the t times 2e to the 3t all together gives us 4e to the 9t and subtract. Minus 4e to the 9t, minus 4e to the 9t, minus 4e to the 9t, minus 4e to the 9t. Grand total is minus 16 e to the 9t. What's the important thing about minus 16 e to the 9t? Good, you've cracked the code. So they are indeed linearly independent. Okay, 2 bullet points down. Any questions? Oh, I was going to make a comment. All right. If you don't like this comment, you don't have to remember it. You're probably thinking like, Steve, is there like a way to simplify taking this determinant? That would be cool, Steve. Like, yeah, man, we can totally do it. Okay. So sometimes when you're taking these determinants, you might just say, hey, you know, it would be nice if we could pull stuff out. And you actually can. And here's how it works. It's a very simple idea. Because whenever you take a determinant, you always have, you're taking these products, and every term, every piece of your product involves something from each row and something from each column. So what you can do is you can say, hey, if I have a common term in a row or a common term in a column, I can pull it out. So is there anything common in the first column? E to the t. So I could have pulled that out. And then I'd be left with 2, 2, 1. Is there anything common in the second? E to the 3t. So I could have pulled that out. Is there anything common in the third? E to the 5t. So I could have pulled it out. So e to the t, e to the 3t, e to the 5t is e to the 9t times this determinant, which for some people are like, that seems better. But wait, we could go even further, right? Why not? Does this row have anything in common? Does that row have anything in common? 2. So we could pull out row stuff too. So 2, 2, e to the t, e to the 3t, e to the 5t, 1, 1, 1, 1, 0, minus 1, 1, minus 1, 1. And now, probably people would say, that seems like a much simpler determinant. And it is. But you'll get the same answer. So anyways, that was the comment. That was the comment. So, but make sure if you're doing this, you know how to follow the rules. You can pull out a common term. I'm writing this down, so from a row or a column. So this isn't scaling. I just want to point this out. Scaling says you pull it out from all the terms. This says you pull it out from just a row or just a column. And the determinant will be left as is. All right, so what's left for us to do to finish this problem? Find x. Okay. Cool. So how do we find x? Someone made the comment, it's easy. It's like, circle it. It's here. We found it. Well, no, that's not what it means to say find x. Right? What haven't we done yet? Like, what hasn't been used? Initial values. And you're thinking like, it's too bad we ran out of paper, Steve. Well, good news for you. We have more. Just when you thought we were out, we find more paper. So we know that we have linearly independent solutions. And because there are 3 entries and there are 3 linearly independent solutions, that says, look, we have everything we need. We know we have a particular solution. So that says our general solution looks like some multiple a, 2e to the t, 2e to the t, e to the t, plus b, 2e to the 3t, 0, minus e to the 3t, plus c, 2e to the 5t, minus 2e to the 5t, e to the 5t, plus the particular solution, 3t, 5, 2t. So every solution looks like that. Every solution. And we need to say, what's the one? What's the one that looks like 8, 21, 0? Okay. So, how do we figure that out? We plug in 0. Right. So, we proceed. So we have 8, 21, 0 equals A, 2, 2, 1. Nice thing is e to any power is just 1. Then B, 2, 0, minus 1, plus C, 2, minus 2, 1, plus 0, 5, 0. So we plugged in 0. All right. Now, at this point, what do we need to do? Okay, so there's something about coefficients. What are we doing with the coefficients? Distribute them? Okay, so one thing is, this looks like one equation, but it's actually secretly 3 equations. And here's the 3 equations. Look at the top entry. You have 8 equals 2a and 2b and 2c. I'm just reading off the top entries. And remember to scale, because like the a comes in. The second equation, 21, is 2a plus 0b minus 2c plus 5. The bottom equation, 0, is equal to a minus b plus c. So we have 3 equations. We have 3 unknowns. That's a good number. They match. We have a chance, a real chance. Actually, more than a chance. We're guaranteed success. They might say, how are we guaranteed success? The Wronskian told us we'd succeed. So we know we're going to succeed. All right. So 3 equations, 3 unknowns. We can probably clean it up a little bit. Can we do anything to this first equation? Divide by 2, right? Yeah, so this, we can clean it up. A plus B plus C equals 4. The second equation, well, we can move the 5 over and then divide by 2. A minus C would equal 21 subtract 5 is 16, divide by 2 is 8. And then A minus B plus C equals 0. All right. Any suggestions? Things we can do to make our life better? Okay, so we can do lots of things. So one suggestion: eliminate a coefficient, do substitution, and there's methodical ways you can do this. But really, we just need an answer, right? So I often say, is there anything that's really close to being the same? Are any of these 2 out of 3 equations like really close? The first and the third are really close, like really, really close. What would happen if we added the first and the third equations together? 2a plus 2c would have to equal 4, right? So you're like, oh, a plus c has to equal 4, but what else do we know? A minus C has to equal 8. That's the middle equation. Well, what would happen if we added those together? 2A would equal 12. So what does that say about A? 6. What does it tell us about C? 6 plus C equals 4. So C is -2. What does that tell us about B? Well, come back here. We know A plus C has to equal 4. So A plus B plus C has to equal 4. So what does that say for B? That should say that B should equal 0, right? Let's see. Does everything work? I think I've made a mistake. Where's my mistake? A plus C equals 2. Haha, classic, Steve. But I could see that B equals 0 wasn't working. So that's good. All right. So 2A equals 10. So A equals 5. So C equals... So if A plus C equals 2, then C should be -3, right? And if A plus C equals 2 and A plus B plus C equals 4, B equals 2. So our answer, x is equal to 5, 2e to the t, 2e to the t, e to the t, plus 2, 2e to the 3t, 0, minus e to the 3t. And then minus 3, 2e to the 5t, subtract 2e to the 5t, e to the 5t, plus 3t, 5, 2t. Whew. Whoops. That doesn't look like a 2t, does it? There we go. Done. Done. Okay. And that only took us a lot of time. We still have at least a third of class left. Any questions? X prime equals this x. Verify that these are solutions. Verify they're linearly independent using the Wronskian. And write the general solution to this differential equation. All right, first bullet point. Are they solutions? Let's just go with yes, no. Yes. Second bullet point, number 2. What's the Wronskian? 5t squared. Are they linearly independent? Yes, as long as you avoid 0. Because where the Wronskian is 0, things break down. So solutions break down where the Wronskian is 0. That's still the same philosophy. How do you write the general solution to the differential equation? Ooh, was that the tough one? Okay, so they are solutions. The Wronskian is 5t squared. And once you know that they're linearly independent solutions, the general form is an arbitrary constant times the first, an arbitrary constant times the second. Every solution looks like that. So general form means what you would have from that superposition. So that's what you're after when you're looking for general form. All right. Good. Well, now that we've done our warm-up for today, we can talk about the real ideas, which is to say, look, we're going to move away from examples like this. This is not going to be the thing we like to do, because here, this is a matrix which varies with t. We're actually very much interested in things where we don't vary. So that's constant coefficient, constant entries. Now, the old idea, way back, like from 2-3 weeks ago, that was a long time ago, was saying, hey, our solutions look like e to the lambda t. And then we just got to find that right value of lambda. That was what we used to do. And now we're like, our new idea. Let's use the old idea. And say, hey, our solutions basically are still like e to the lambda t, but now it has to look like a vector. So we're going to multiply it by a vector v. Shoo, shoo, shoo. So v e to the lambda t. All right. Well, so now we've kind of doubled our work. See, because now we have to figure out v and lambda. Previously, it was a little bit easier. All we had to do was figure out lambda. So it's like now there's twice as much for us to figure out. Okay, but that's not too bad. We can kind of see where we're going. So we say, all right, we do what we did before. We plug it in. X prime equals ax. And we're guessing that our solution looks like e to the lambda t times v. All right. Well, to take the derivative, that just brings down to lambda. So here's our x prime. So this is our x prime. Here, this is our ax. Well, they both have e to the lambda t, so you can cancel. And we say, aha, what we're after. We want some vector v such that when I take a times v, the result is v scaled by this number lambda. All right. Well, it would be nice if people had looked at this problem. Well, good news. This is something that's been extensively studied. So they call the v here, this is what's called an eigenvector. And the lambda is what's called an eigenvalue. Now at this point you might be saying, okay, so what's an eigen? It's a German root. It basically, you should think of it as meaning the same. So this goes back to the notion of what does a matrix represent? It tells you how to change from, like we talked about matrix multiplication, you go from the x to the y's to the z's, and so forth and so on. So a matrix says, how are you changing? And it says, well, if you try to say, well, how do I change in this direction? It says, oh, it's a very simple change if you go in that direction. You just are scaling. So that's why it's sort of the same direction. That's what is going on. Okay, well, so how do we find these magical things, these special eigenvalues and eigenvectors? So we start off saying, all right, we know what we want. We want this relationship. Well, let's get some zeros involved. So we subtract the lambda v across. So 0 equals av minus lambda v. Perfect. And then for some mysterious reason, we put an I here. They might say, why did we do that? And our response is, why not? No, actually our response is, what would you like to do? Well, you like to say, I'd like to factor the v out, because the v is common. But if I factor it at this stage, I'd have a minus lambda. And that's just nonsense. But if I factor here, I get a minus lambda I, which is fine. So that's why I put the I there. All right, so we're looking for something where a minus lambda I times v equals 0. So essentially we've just restated that formula. Now here's the magic. We need to make sure that there's some vector that's non-zero, because 0 is not very interesting solutions to differential equations. Some non-zero vector that does that. And now that's only possible if the determinant of a minus lambda I is 0. So, idea. How do we do this? Here's the method. Finding eigenvalues. So, we start with a matrix. We set up a polynomial by writing down a minus lambda I, take that determinant, and set it equal to 0. This is called the characteristic polynomial. Now, I will get in trouble with certain members of my department where I write a minus lambda I, and they will say, tisk tisk on you, Steve. It should be lambda I minus a. Yeah, forget it. Okay, don't worry about those people. We don't pay attention to them. All right. So that's how you do it. So we're going to do an example. Find the eigenvalues of 4, minus 7, minus 3, 6. Okay, so this is a 2 by 2 matrix. Now, there's a fact, which I haven't said, but I'm going to tell you right now. If I have a 2 by 2 matrix, I will always have 2 eigenvalues. If I have a 3 by 3 matrix, I will always have 3 eigenvalues. In general, if I have an n by n matrix, I have n eigenvalues. Now, I am allowed to repeat eigenvalues, and that's going to be a really interesting discussion for Friday. That's, if you think things are good now, wait till Friday. That's when we're really going to get into the good stuff. All right, so here is A. So we're going to take the determinant of A minus lambda I and set it equal to 0. All right, so that says we're taking the determinant. We subtract lambda off the diagonal terms, and everything else stays as is. Okay, so that's our determinant. So 2 by 2, that's not too bad. We've got our 2 diagonals, and we just have to patiently work it through. So we're going to get 4 minus lambda, minus 7 minus lambda, subtract 6 times negative 3. Right? So diagonal, subtract diagonal. We expand. In the first part, we'll get lambda squared. Right? Minus lambda times minus lambda. Minus 4 lambda plus 7 lambda will make plus 3 lambda. 4 times minus 7 makes minus 28. Minus 6 times negative 3 plus 18. So far, so good? Lambda squared plus 3 lambda minus 10. Which is why we're going to always end up with whatever the dimension is, that's how many eigenvalues we are, because it's always going to reduce down to a polynomial. So finding eigenvalues is about finding roots of polynomials. And now you're like, that's why they had us work on that for 5 years when we were kids. One day it was going to pay off. And that's this semester. All that work paid off. Well, does this factor nicely? Yes. What does it factor as? Lambda plus 5, lambda minus 2. So, what does that say our eigenvalues are? They are negative 5 and 2. Now, there's a tip here. It says you can check if you did it right. Here's the check. Add up your eigenvalues. What do you get? Negative 3. Add up the diagonal entries. What do you get? That should always match. If they don't match, mistakes were made. Multiply your eigenvalues. What do you get? Negative 10. Take your determinant. Minus 28. Subtract negative 18 gives us negative 10. They should always match. So the sum of the diagonal is always the sum of the eigenvalues. The determinant is always the product. So you have ways to check. All right, we will stop here and pick up again next time.